This is a topic called fluid dynamics, but we're going to start with just some properties of fluids, and the PowerPoint's called Fluid Properties 1 on Moodle. And as you can see on the first slide here, these are the things we're going to have a look at in terms of fluids. So we're going to start with just looking at some properties of fluid. So if you've got a fluid, a gas or a liquid, what are some of the things you want to be able to measure? So how heavy is it? How sticky is it? How fast does it flow? Does it go up or down? There's a whole lot of things you want to think about just the property of a fluid. Why is water different from oil? They're different fluids. How is honey different from air? They're both fluids, but they're quite different things, assuming the honey hasn't been left in the fridge and turned into a solid. Okay, so runny honey. So yeah, how are those things different? So that's what I mean by properties of fluid. And then we're going to have a little look at pressure, which is what we're going to use most of in the engineering context. We're going to be figuring out about head of pressure and figuring out how much pressure there is at the bottom of a reservoir and things like that. The idea of gauge and absolute pressure is a measurement thing. And then we're going to have a look at submerged objects, so particularly maybe like the face of a dam. So if you're going to be doing some design work and you've got a dam full of water, how much force is pushing on the dam? Okay, so that's just a summary of the topics we're going to look at. So I think we're going to start with properties of fluids. So here's some words that we use. So mass, weight, volume, and density are the key things, and most of these you've come across before. And so just thinking about these, what are the units going to be? So the units of mass is, altogether, kilograms, okay? So mass in kilograms, weight in newtons, okay? That's just the normal mass times 9.81 gives you the weight, that's cool. Volume is going to be in cubic meters, yep. Okay, so volume we're going to do in cubic meters. And here's the first bit of information, something you do need to know, which is that one, brand new pen, go, 1 cubic meter is 1,000 litres. Okay? And in terms of engineering things, mostly we are going to be working in cubic metres. You're going to design a dam, you don't really care how many litres it holds, it's kind of a small unit. So a lot of engineering things are in cubic metres, especially in a civil environment. So often cubic metres, but 1 cubic metre is 1,000 litres. It's definitely something you're going to worry about. And then we're going to have this property, density. And density is mass divided by volume. Okay, so it gives us an idea of, again, it's not one of these words that's not used well. So you would say something like, oil is lighter than water. It's a sort of phrase you hear people using all the time. What the correct technical thing is that oil is a lower density than water. Because if you've got a cup of oil, it's not lighter than a teaspoon of water. It's heavier. It's got more force. It's got more weight, hasn't it? You've got a lot more of it. So when we're talking about one floats on top of the other, it's per cubic metre that you're interested in. Okay? So density is in kilograms per cubic metre. Yep, okay. So that's a really important property of a fluid, is how dense it is, kilograms per cubic metre. Okay, and we talk about specific weight, which is just, instead of mass, it's weight. So it's just exactly the same idea, but with 9.81 in. So we're doing it straight into newtons. Again, it's a force-related thing that we're interested in. And the bottom one there, specific gravity. Specific gravity or specific density, you'll hear it referred to, is the density compared to water. So the specific density of water, specific gravity of water, is 1. Okay, so for water, technically fresh water, yep, at a particular temperature as well, at 4 degrees Celsius. So yeah, you're right. There is a very precise meaning for it. So fresh water is 1. No units, it's just saying water is the base thing that we're comparing against. Whereas something like oil might be about 0.8. which means that the same volume of oil and water, the oil has only 0.8 of the mass of the water. And to turn this into actual numbers, like how many kilograms per cubic metre, you need to know one crossover point. And the idea with water is that water is 1,000 kilograms per cubic metre. Okay, so if you've got a cubic metre of water, it's 1,000 kilograms, which comes back to 1,000 here, because a cubic metre is 1,000 litres, and it's also 1,000 kilograms. So it follows that water is 1 kilogram per litre. Okay, so this would tell us that oil will have a density, so the density of oil would be 0.8 of the density of water, which is 0.8 of that 1,000 is 800 kilograms per cubic metre. Yeah. So as long as you know what these numbers are, these relative density, specific gravity, there's a whole lot of names for it. You can look those up on tables, again, like Engineering Toolbox, there's a big list of them, and it'll give you these numbers. And then you just multiply them by 1,000 for water to get the actual density for each one. Mercury about 13.6, yeah, exactly, yeah. So that means that mercury would be 13,600 kilograms per cubic metre. Okay, so for each substance, you can look that up. And these figures are available not just for fluids, but for solids as well. You can tell how dense steel is. You can look it up and get a number for steel, multiply it by 1,000 for the comparative to water, and you'd end up knowing how many kilograms a cubic metre of steel would be. Okay, so relative density, specific gravity. And then I slipped in, when no one was watching, I slipped in a row, just because I could. So density, the symbol we're going to use for density is this rho. Another one of these Greek letters, I've had a few of them. It's a rho, that one, spelled R-H-O. It's the Greek sort of R sound. Okay, so rho is the symbol, density is the name, units, kilograms per cubic metre, and water is the key one at 1,000 kilograms per cubic metre. Okay, so those are the basic properties that we need to be able to measure when we're trying to figure out basically how much stuff we've got. And then we've got some fun things that we have a look at. So here's surface tension, is something which you'll have heard of. So here's the ability to do with how the particles bond in a fluid, and you can actually hold the force on the surface of something. So you can float a paper clip, or little bugs can walk on top of the water, because the bonds in the surface are different between the bonds within the material are different from the bonds at the surface where there's another material bonding onto it. And I think I've actually got some examples of how that can be used. So it's used in soil mechanics. So when you do geotech, for example, you'll talk about water being able to be drawn up. So if you have a dry soil and you put water at the bottom of it, eventually the top will get wet, okay? Because the soil can draw the water up through the soil. Clearly, if you pour water on the top of something that goes down, gravity works that way. But this has the ability to work against gravity effectively. There's enough force there to be able to lift the substance up through things. So you see it in a meniscus, so a curve on a capillary. So your capillary is the word for a thin channel. Like you talk about capillaries. You have veins and things that go in the very thin bits called capillaries. So capillary is just a really thin tube. So capillary action here is because the bonds on the outside where the fluid's joining the glass or whatever it is are strong enough to be able to just draw it up slightly. So you get this idea of capillary action. On this course, there's not going to be any calculations or anything involved in that. It's just an idea that surface tension matters. Viscosity has a whole lot of things, and this does matter. I have seen old exam questions that talk a little bit about viscosity. So viscosity is great fun, and I think I've got some videos linked to this. This works? Or? Yep, it must be. How do I've got videos linked to these, or? Okay, I clicked it, and the mouse has gone away. So let's come back. Here we go. Can you see the difference between the two things? So to go back to the start. So this is one thing like water, and this is another thing like some sort of jelly stuff. And when they shook them, they behaved quite differently. So the one on the left was a lot more faster, flowy, sort of moved a lot more. Yep. And the one on the right is a lot thicker and slower. So the one on the left has low viscosity. Yes, yeah, there's probably something about flow of water through a pipe, yep. So water would have a particular flow, it flows in a particular manner. So basically, if we have a viscosity measure, and at this end we have low, and at this end we have high viscosity, then things that you associate with, they're thin down this end, and thick down that end is sort of the language that you use when you watch those two pictures. You said the one on the left was thinner and the one on the right was thicker. So viscosity is what is measuring those things. And we should be able to see what else happens when you do this. Because this is pouring a low viscosity fluid, and this is pouring a high viscosity fluid. Yep. Okay. So other sort of words you use is that this goes faster and this goes slower. Yep. Medium is the thing that it flows through. Yeah. But you get the idea that they're to do with flow rates, how fast they flow, how easily they flow. So the low one also, if you look at the difference between the two when they've been poured, so that's the thick one towards the end. Here's the low one right near the end. Okay, so that's the low viscosity one, right at the very end of the pour. Okay, so that's the low. It's still at the very end of the pour. It's still got a lot of mixing going on in it. So even when the fluid's hitting it, it's mixing it up a lot. Whereas the high viscosity one, right at the end of the pour, if I can get somewhere, do we see the end of the pour? No, let's go back to get it. No, it's gone up. Come on, where's it? Okay, here we go. That's a pretty good shot there. Lost it. There. Okay? You can, Dave, come on, I had it. There. Okay? You can see how it's settled out at the bottom. So the mixing's happening only in that top layer, and then underneath that it's a lot more settled. Yeah? So the low viscosity has what's called high turbidity. It's a lot more turbulent, and we'll talk about turbulence in a second. So low viscosity has higher turbulence, and high viscosity has lower turbulence. I have definitely seen exam questions that have asked you sort of these sort of questions. So a low viscosity fluid is likely to have high turbulence, true, false, that sort of question. Okay. How do I get back to the next thing I was going to click on? Flowing viscosity, what's this about? Oh, cool. Okay, so this is, you can see they're pouring stuff into so the four mediums, the four substances are different viscosities. What's going into them is the same in each one. And you can see quite different viscosities. So the one on the far right is very, very low viscosity. So it's like if you pour something into water, it'll go like that, and then backwards to a very high viscosity on this end. It's basically the stuff doesn't even go into it. It's too thick for it to get into. And the other ones in the middle, it gets in, but it keeps the blob shape effectively. It doesn't have that turbulence to break it up. It stays as a blob. Yeah. What else have we got? Just trying to get these mixing viscosity. Oh, this is my favourite one. It's got volume on this one, I'm sure it does. This is awesome. This is great fun. We'll try and find some volume. On, off, that might help. Let's start again. Okay, so what the story is it's sort of self-explanatory, apart from the fact the guy can't count, which makes it seem a bit weird at one point. So basically it's a cylinder that he can turn around, and he's putting fluid into it, and you'll see what happens. It's quite entertaining. Okay. So the white stuff is a high viscosity fluid. So it keeps its shape, there's no turbulence. Stays in its shape, doesn't it? Because it's high viscosity, it doesn't have any turbulence to muck it up.
Right, now we're going to rotate these fairly
Counting.
5 times.
1. Where he started? No. 2.
Notice the flow is laminar because the wells over
3. 4. 5. 6. 6.5. He did 6.5. And he's going backwards. 1. 6.5. It's gone back to where it started from because there's no turbidity. It's a high viscosity fluid. So what happens, it's what's called laminar flow. So when it flows, it stays all on the exact lines that it was in. I'm sure, you can't see it, but I'm sure if you look down on top of it, it would have been, I suspect he went red, green, blue, so that when he spun it, they were on different tracks. I strongly suspect that would be the top view of it. But even so, it's still pretty cool that it comes back. When you spin it back, it comes back as a blob. Because when they went round, there was no turbulence, there was no mixing, so you don't get it suddenly going out and drifting all over the show. It just goes on that track. And when you wind it back, it winds back on the same track. Yeah? And you end up with that amazing thing. It's really, really cool. But that's because there's no or very little turbidity. So very low turbidity with high viscosity. So with high viscosity, we have what we call laminar flow. Things just stay in the lines that they're put in. No mixing. Yeah. So over here, low viscosity tends to have lots of mixing occurring. And if you ever want to have a think about what people think about science, you need to read all the comments on that video. They're hilarious. Most people trying to say it's a fake video, it's just a thing run backwards. The fact that you can't count is taken as evidence that it's all a fake. It's fake. It's clearly a fake video if you read the comments. It's legit, it's perfectly legit. But you read the comments on it, And people that don't understand science and sort of like conspiracy theories will tell you that it's faked, or it must be faked because it's not something they can't understand. Therefore, it's a fake. Um, it's not fake. It's legit. It's perfectly legit. Well, that's probably pretty much life, I think, Liam. People deny things that are real because they don't understand them, and same people accept
One
it.
of the physical water quality parameters that we monitor at Utah Water Watch is called turbidity. Turbidity is the amount of suspended material in a stream or in a lake. This can be sediment, such as soil, or plant material like algae particles that are in the water. Basically, turbidity is a fancy word for water clarity. In the stream, we use what's called a turbidity tube to monitor how clear the water is. If you look at this tube, it has a ruler on it with centimeters, and way down at the bottom is a white and black disc. We fill this tube all the way up with water, and then we can lower it to the level where we can just start to see the white and black disc. That tells us how clear the water is. So the first step is to go into the stream and to fill it up. Go to your monitoring location, and when you're at your monitoring location, you want to sample the water that's coming from upstream. You don't want to sample the water downstream after you've stirred up the sediment. Take your turbidity tube. You don't want to sample right at the surface, just right below, a little bit below the surface, so stick it down underneath, and then put the whole thing up and let it start to fill all the way to the top. Now once you've filled it all the way up, you want to make sure that you can look through the tube and be able to see. If you can fill it all the way to the top and look through the tube, then you will record that the whole water column is clear. So what this means is, on your data sheet, you would select the greater than symbol and write down 60 centimeters. Because in theory, if I have a longer tube, I could keep filling this tube up to increase the clarity of the water. So this is what happens when you have very clear water, very clear stream. Now let me go demonstrate if you're on a different stream, such as like the Colorado River or the Green River, that naturally have a higher sediment, a higher turbidity to the water. So now for demonstration purposes, I've artificially increased the turbidity, stirred up the water so we have all this suspended sediment. So now when I look down through the tube, I can no longer see the white and black disc. So now we're just letting the water drain out just so we can start to see the outline of the white and black disc. You want to make sure that you do this in an even amount of light, so either all sun or all shade, and right there. Now when I look down, I can just start to see the white and black outline. So then I would go on the scale and look. We have 10, 20, 25 centimeters. So this
Don't even need to watch them counting centimetres. But you get the idea. It's the word turbidity in terms of water clarity. So stuff that's more mixed up and it's holding more sediment is more turbid. Slightly different from the word turbulence. No, that could be both in freshwaters. You have two completely different freshwaters that have different turbidities. It'll do with what they've been running through. So rivers that have been running over nice smooth pebbles with not much in them will be very clear, and water that's been running through a clay base where it can pick up lots of fine sediments or algae and stuff like that will have a lot less clarity. You can go to Lake Waihola and do it. It's quite different on two different days. Okay, here's this idea of laminar flow again. This is the last little video. So here we have a flume like the thing we've got downstairs, hopefully, and you can just see, if you speed it up, start putting it through faster and faster, you can see the point where it's on the flow. Yeah, it's got turbid now. It's lost that laminar flow. It's got quite turbulent. it's just a noise, a mess of noise. So the speed will affect how laminar the flow is as well. Okay. So just all these concepts, and at this level we're just trying to introduce some words, give you the basic concepts for some of these properties. And the exam question is basically going to be knowing which concepts go together, if there's an exam question at all.